This video will cover section 6.2, the law of cosines. And the objectives for this lesson will be to use the law of cosines to solve oblique triangles. So we're talking about not right triangles. And it will be for triangles in the form SSS, meaning that you are given three sides, or SAS, meaning that you are giving a side, two sides, and the angle in between them. That's why the letter A is positioned in between it, and we refer to that as the included angle. So we're also going to use the law of cosines to model and solve real-life problems. And then finally, for the section, we will use Heron's area formula to find the area of a triangle. In the previous section, 6.1, we covered law of sines, and the law of sines is useful to find all the measurements of an oblique triangle whenever you are giving other types of measurements. For the two that we see here, we will use the law of cosines. Also in section 6.1, we looked at a way to find the area of an oblique triangle. So the one that we have here is not the same, it's going to be a new one. Okay, so the two cases that we did not look at in section 6.1 is when you have, I already mentioned that, SSS or SAS, and that refers for three sides given or two sides and their included angle, SAS. And here, none of the ratios in the law of sines will be complete, or it will be impossible if we were to have those measurements. In such cases, we will always use the law of cosines. So here, this is going to be part of your formula sheet for next exam, I guess, exam 3. And we have here the standard form of the law of cosines if you were to be asked to find one of the remaining sides. So if you look at it here, the three of them, you have a square, b square, c square. Recall that lowercase letters are used to denote sides, and the uppercase letters are used to denote angles. So for the standard form, you are going to find sides. Of course, that once you complete the operation on the right side, you will have to take the square root because you want to find what a is, not a square. So similar to Pythagorean theorem. So all three of those are to find the sides, and the three that we have here are to find angles. And you could see that because we have A, B, and C in uppercase letters. And so for those, of course, you will have to take another step and take the cosine inverse to find the actual angle. So the formula, it will be cosine inverse of the expression that you have here on the right side. And so if you look at the one that I'm about to write, I have angle A. I'm looking for angle A. And so the variables that I will be using here for length, it will be b squared plus c squared. Those are the letters that are different to A. And then we will subtract the measurement that is opposite to angle A, and then we will square it, or square the square. I'm sorry, subtract the square of that side, because first we square. And then on the bottom, we will have the denominator 2 times, and it will be the same as the two angles or two sides that we have here, but without squaring them. So it will be 2 times B times C. And that is how we will find the angle A, of course. So we're going to learn how to enter all of this on the calculator at once. And I just want to point out that if we are looking for angle B, for example, we're looking for angle B here. And of course, we will have to do the cosine inverse of the expression that we have here. But I want you to notice how now the two sides that we're squaring and adding will be the other two letters that are not the same as the angle. So for example, A and C. Then on the bottom, we have the product 2 times angle A times C. And I'm sorry, not angle, but side. And so again, it's the two sides that are not opposite to the angle that we're actually looking for. Similarly, if we're looking for angle C, uppercase C here, we will be adding the squares of A, so the other two letters other than C, and also B. And then, of course, we subtract the square of the angle that is actually opposite to it, just like we did here as well. And then the bottom is going to be twice the product of the two sides that are not opposite to angle C. Now, if we go back to the formulas on this side, on the left, you could see that this part, it looks kind of similar to, maybe this one is the one that looks more similar, to the Pythagorean theorem, because we have c squared equals a squared plus b squared. But remember that Pythagorean theorem can only be used with right triangles, and here we're talking about oblique triangles, and so that's why we do all of this. We have to include that part. Also, if we're looking for A or B, we're not going to have a subtraction, a minus here for the squares. It's always going to be a plus. Okay, so moving on. I'm not going to derive the formula because I know that you guys don't even watch my videos, so I'm not going to waste my time doing that. So let's start with example 1, and example 1 is one of those cases where we are given all three sides. So we have side A is equal to 8 feet, and then we have side B, which is equal to 19 feet, and then finally we have side C that is equal to 14 feet. And so if you look at right across from each side, we could see the angle that is opposite from that side. It will have the same letter but uppercase. So for side B here, we have angle B, and then for side C, we have angle C. So find the three angles of the triangle shown below. So the question could also be worded like solve the triangle, meaning like find whatever is missing. So in this case, we got to find all three angles. So let's start with one of the angles. So I have already copied the formula here. And so what I'm going to do is go ahead and write what we need to do for B, which is going to be a square. Well, actually, it's going to be cosine inverse of a square plus c squared minus b squared. And everything is divided by 2ab. So I'm going to substitute, and we start with cosine inverse, of course. And then we're going to substitute our numbers. So for a, we're going to have 8, and then we're going to square it. Then for c, it's going to be 14. And we're going to square it. And then we need a minus because we have a minus in the formula. And then we're going to need b squared. So the measurement for b is 19, but we have to square it as well. Then we're going to divide everything by 2 times a, which is 8, and b, which is 19. So we could see all of that. A is here and here. And actually, this is wrong. It shouldn't be 19. I need b And no, I wrote the formula wrong, actually. The formula should have C over here, just like it does there. So be careful with that, don't do what I did. And so side C is actually 14. So we're going to enter all of this on the calculator at once. And for that, we're going to need an extra set of parentheses, which are going to come from here, or they will be placed there and there. And that will enclose our numerator. And similarly, just in case, I'm going to use another set just to enclose the denominator. And of course, we still have to have the two parentheses, one to open the expression for cosine inverse and another one to close it. So I'm going to open the calculator. We have to enter cosine inverse first. So second function and then cosine to have cosine inverse. That first parenthesis is comparable to the one that opened in purple here on the left side. Then I'm going to enter another one that will be representing the one in pink here. And then I will continue with 8 squared. So number 8, we actually have a button to square something. It's right there. And then we're going to add, I believe side C is 14 square. 14 square and then minus, and that will be B square, which is 19. So 19 square. And we close the parentheses. That one is closing the one in pink that we have here, so that we have our denominator together. Then we're going to enter the division sign. And then just to make sure we do it correctly, let's open a parenthesis to also enclose the denominator. So it will be here. And we're going to enter 2 times 8 times 14. So 2 times 8 times 14. We close that to close the denominator. So that will be this parenthesis here. And then we're going to close one more time to enclose the whole expression that goes inside cosine inverse. So going back to the calculator, so one more parenthesis to close. And then we are going to press enter. Now, if you notice, my calculator says radians here. And even though this is not telling me what to do, typically for these two sections, 6.1 and 6.2, we use degrees. So I'm just going to change it to degrees. Remember, I have to go to mode and then make sure that the word degree is the one being highlighted. So I use down arrow one more time, one time to the right, and then I'm going to press enter. And now I can go back to my main screen and then press enter to do this calculation. So I changed to degrees. Let's round it 1 decimal or to the nearest tenth, which is 1 digit after the decimal point. So it's going to be 116.8. So that means that angle B is 116.8 degrees. Okay, now let's go ahead and find angle A. So now to find angle A, I'm going to use the formula. I'll show it to you. The one that we have here, but we're actually going to solve for A, so then it's going to look like the one, oops, I moved that, like the one that we have here. And so we will be actually using this formula. So the formula is cosine inverse of the fraction. And we have, since we're looking for angle A, we're going to need B squared plus C squared minus A squared, and then divided by 2 times B times C. So let's go ahead and substitute here. So for side B, because it's lowercase, so I need the side, I'm going to need a 19 from here. So 19, and then I'm going to square it. Plus, side C is 14, so 14, and then square it. Minus a square, which is 8, so 8, and we square it. Now on the bottom, we're going to have 2 times B, which is 19, times C, which is 14. Now we're going to enter all of that on the calculator at once. And I might have to go back and forth, but that's okay. So remember, first is cosine inverse. Then we open another parentheses for the numerator. Now let's go ahead and enter the numerator, 19 squared plus 14 squared. So 19 squared plus 14 squared minus 8 squared. Close parentheses to enclose the numerator. There we go. Now divided, open parentheses to enclose the denominator, and that will be the product of 2 times 19 times 14, close parentheses, to enclose the denominator, close it one more time to close the cosine inverse expression. We make sure it's in degrees, our calculator, then we press enter. And that is our solution. 22.07. So we say we're going to round one digit after decimal point, so it will be 22.1. So angle A is 22.1 degrees, and that's the one here, 22.1. Which one do we find? B. Angle B is here, and so that one is 100. And if you notice, it does look obtuse. So 116.8. Now for the third angle, since we already have 2 of those, we don't have to use the law of cosines. Instead, what we could do is subtract the 2 that we had already found. And I see that they were rounding to 2 digits. So let's go back. And it will be, because we have a 0.075, and on the PowerPoint it says 22.08. So I want you to make sure you know where that 8 came from. So the third digit is a 5. That makes the 7 go up. So we're going to use, instead of that, we will use 22.08. So make sure you read how WebAssign wants you to round. So now to find the third angle, we have A, we have B. The only one left that we don't have is C. And remember, the interior angles of a triangle are always 180. So that's why we start from there. We subtract what we found for angle A. You can see it here. And then we subtract what we found for angle B. And that gives us angle C, which is 41.12. So I'm just going to go back up here and write it down. So angle C is 41.12. The little markings that I do on the angles is just to denote that they're not equal. Even though it's pretty obvious that they're not, it's still good practice. You can notice that the longest side here is 19 feet, and it is opposite to the biggest angle, the obtuse angle, 116.8. And then the smallest angle is 22.1 degrees, and that one is opposite to the smallest side, which is 8 feet. And then lastly, you could see that the side that is in the middle, if we compare them in terms of measurements, it is 14, side C, and that is opposite to the angle with the measurement that will also be in the middle, 41.12. So that is not a coincidence. That always happens that way. Okay, so for this introduction slide, I'm gonna just read from it. So it says, do you see why it was wise to find the largest angle first in example I'm sorry, where was that? In example 1, knowing the cosine of an angle, you can determine whether the angle is acute or obtuse. That is, if the cosine is positive, we are talking about an acute angle. How do we know that? Well, because in the xy axis, the cosine in quadrant 1, remember the x's, cosine of theta is related to the x coordinate of the point. And so the x coordinates are positive in quadrants 1 and 4. However, we're not going to have an angle that is bigger than 180 because then it wouldn't be a triangle. So that's why we're only concerned about quadrant 1, the angles that go from 0 to 90. And then if the cosine is, so that was if the cosine of an angle is positive, greater than 0. And if the cosine is less than 0, meaning negative, that means that we're located in quadrant 2. And so that will tell us that we have an angle that is bigger than 90, so it will be an obtuse angle. The terminal side is in quadrant 2. And that happens when the cosine is negative, because remember, cosine is related to the x coordinates, and that in quadrants 2 and 3, those coordinates are negative. However, we only stay with quadrant 2 because if we're talking about triangles, it makes no sense to have one angle that is more than 180. In fact, the sum of the three interior angles cannot go over 180. It needs to be exactly 180. And so that's how you know that you have an obtuse angle, if the cosine is negative. If the cosine is positive, again, that means that you have an acute angle, an angle that will be greater than 0, but it will always be less than 90. It could be like 89 point something, but it will never be 90. Okay, so in example 1, once you found that angle B was obtuse, you knew that angles A and C were both acute. It also helped that we had the drawing of them, but you will not have the drawing at all times. Furthermore, if the largest angle is acute, then the remaining 2 angles are also acute. So if one of the angles is obtuse, the other 2 will be acute. If the first angle you find is acute, the other 3 are acute. So we're going to use the law of cosines to solve this application problem. So example 3, I'm going to read it. The pitcher's mound on a women's softball field is 43 feet from home plate. So the pitcher's mound is positioned in the center of the baseball field or softball field. And it says that it is 43 feet from home plate. So here is your 43 feet. And you can see we're not using the letters A, B, C. We're going to be using the letters P, H, and F. I assume H is for home plate, P is for pitcher, and then F is going to be for first base. Okay, so moving on, I'm going to go ahead and color that angle F blue. And you can see the side opposite to it is the one here with the lowercase f. That's 43 feet. Then it says here in the distance between the bases is 60 feet. So from home to first base, that could be considered a distance, and it is equal to 60 feet. So right here. And so let me actually, I want to match the color. So that will be the distance between bases. And I color that or highlighted that yellow because that's what I'm saying about the angle opposite to that side. So we're gonna, that will be labeled with lowercase p, and it's 60. Then, so that will be 60 feet. And the pitcher's mound is not halfway between home plate and second base. So we cannot assume that the distance, like if we were to draw a perpendicular line here, we cannot assume that the distance here is the same as this, because it says here it's not halfway, so it's not at the midpoint. Okay, so let's go ahead and color the home plate angle and then H right here. Okay, so I know it's not given to us here, but the position where the pitcher is and the angle to which it intersects the home plate, if the distance of it, well, first of all, we know that we have a square here, so we can consider that a right angle, or actually you could see that here, a right angle, right angle. So the line that we have here for the distance from the pitcher to home, it is considered a perpendicular bisector, not a perpendicular, but just a bisector of the angle, which was originally 90. So if we bisect that, cut in half, we get 45. And I know that's not on the problem, it is on the drawing, but you do have a problem like this on the homework. I remember that. So please, if that information is not given, you could go ahead and assume that that is 45. Okay, so going back to the distance and everything, so let's see, where were we? So now the question is, how far is the pitcher's mound from first base? So the question here is for H. That's our big question. So let's see. H is in lowercase, so it's one of the sides. If we look to our formulas, I told you we will use the other two sides first and square them, the addition of them. So f squared plus p squared. Then we will subtract. Actually, I need to look at the formula, I think. Okay, yes. Then we will subtract 2 times the product of those two same sides. So it will be minus 2 the product of f times p. And then we need cosine, and the letter needs to match the side that we're looking for. So it will be, in this case, capital H. So these two, the one here and the one here, need to be a match. The angle that we take the cosine of, and the other two, the other letters will be the letters that are not h. So let's go ahead and substitute what we have. So h squared is equal to f squared, so that will be 43 squared plus 60 squared minus 2 times 49 times 60 times the cosine of the angle that we see here, which is 45. Remember, it's 45 because it is half of 90. It is bisecting, the line from here to here is bisecting the 90-degree angle. So half of 90, 45. Okay, so we're going to enter all of that. In fact, we're just going to put everything inside a square root. And so just to make sure that everything is inside the square root, I'm going to add a parenthesis there. And then I'll write everything. I'll type everything just like we have it here on this slide. And of course, we need to make sure that we will be in degrees. And then I'm going to close the parentheses before I exit out of my square root, or after I enter cosine of 45. So we're going to open the square root symbol first, so second, and then that key. And then we open parentheses, and we are going to need 49 squared plus 60 squared. 49 squared plus 60 squared. You guys see it's important that we're still inside the square root. And remember, the square root is because we're looking for h. We're not looking for h squared. So then after that, we're going to need minus 2 times 49 times 60. So minus 2 times 49 times 60. And then we're going to need times the cosine of the angle 45 degrees. Then I'm going to close parentheses to close the angle of 45. And then I'm going to close last parentheses, and then we're going to press enter. Okay, and you have to make sure your calculator is in degrees because we enter 45 degrees. And so the solution for this will be 42.93. You can see that the answer from the next slide, it says 42.43. But here, what I am assuming is that they enter the substitution that we had done with the 40 square, oh no, what was it? 49 square plus 60 square minus 2 times 49 times 60 and then cosine of 45. So I'm assuming they did that first, and then once they got an answer from the calculator, they rounded that answer. So everything that was missing after the 3 was lost in the rounding process. So just to make sure you get the most accurate answer, that's why I recommend and teach my students how to enter the whole expression at once, because here you're not rounding too soon. You can round at the end, because if the answer must be given by rounding to the nearest, let's say 10th, one digit after the decimal point, this will be 42.9, which is what we found, and I believe that it is more correct. So that was the distance of h. And so it will be 42.9. And so that will be the solution. So I'm not really agreeing with that one. I don't think Voivodstein would actually take it either. So next concept and last objective for this section is called the Heron's area formula. And this name is because it was invented or created by this Greek mathematician with that name, Heron, and who lived 100 years approximately before BC. And so the area, to find the area of any triangle, we take the square root of the products of S times S minus A times S minus B times S minus C. Now, what is S? Well, S is half of the perimeter. Please write this down because I don't want you to get this wrong on your exam. So S is half. You see how we're dividing by 2? So that's what I mean. Half of the perimeter. So you add all 3 sides of your triangle and then you divide by 2. That's what S is. And if you notice, you're going to be using it a lot. S, 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 S. You have it once in the product by itself, and then you have it 3 more times. It is subtracting, you're subtracting one side from it. So right here, let's write it down. S is going to be A plus B plus C divided by 2. So I'm going to substitute. I actually got a little ahead. The example 5 says, using Heron's area formula, find the area of a triangle having sides of lengths 43, 53, and 72. So I'm going to go ahead and substitute that. Remember, I need to add all 3 sides to find the perimeter. And then I'm going to divide by 2 to find the value for S. And so let's see. So 43 plus 53 and 72. Enter, and then we divide that by 2. Don't forget to divide by 2. If you don't divide by 2, your whole problem will be wrong. So this was 168, and then we divide by 2, so we got 84. Okay, now that we know what the value for S will be, we're going to substitute it into our formula here, 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 and here. So we're going to have the area is equal to the square root of the product of 84. And then we're going to write it 3 times. We're going to write 3 sets of parentheses. So 84 minus, 84 minus, and 84 minus. Now, minus what? Well, it will be minus each individual side. So for side A, we have a 43, so that's what I'm going to enter here, 43. For side B, we have 53, so that's what I'm going to enter here, 53. And then finally for side C, we are going to have 72. So 84 minus 72. So we're going to enter all of this on the calculator at once. I just want to remind you that I'm going to use an extra set of parentheses just to ensure that everything is inside the square root. So we're going to do that. First, we're going to go ahead and open the square root. Second, x squared like that, open parentheses. And we're going to start with 84 by itself. Then open parentheses again. Now we're going to enter S minus A. So that is 84 minus, sorry, I have to keep checking, 43. So 84 minus 43, close the parentheses there, and then we open parentheses again because we want to match the parentheses that is here. So the very first one was to open, to start the radicand. And then the next 2 were just to enclose the product 84 minus 43. Now we're going to open another one to represent multiplication, and we're going to enter 84 minus 53. So 84 minus 53, that represents S minus B. Then we have to close that one, just like we have here. And then we're going to open another one to represent multiplication, and that will be S minus C, which is 84 minus 72. So open 84 minus 72, close it to close the subtraction, and then remember one more closing parentheses to enclose the radicand, which is what's inside the square root. So we close one more time, and now we can press enter. So we get here 1131.88. So 1031.88, and then we see here is rounded to 2 digits after decimal. The next one was a 6, so yes, it makes sense. If we round to the nearest hundredth, we only look at this number, the 6, and because it's bigger than 5, it makes this 8 turn into a 9. It goes up. Okay, so the last slide is just a summary of the formulas that we have studied in this section, which is the Heron's formula. And this is when you have all 3 sides and you want to find the area. Or we have the ones from section 6.1, which are with the law of sines, and those were covered there. And that is half of the one of the sides, and then instead of the height, we use this concept C times A, or B times C, or C times B, depending on what you are given. And then the standard formula, the one that you've known since elementary, that one is the same as base times height, and then divided by 2, right? That 1/2 times that is the exact same thing. That one is easier when you have a right triangle, or when they give you the height, even if you don't have a right triangle. So this concludes the video. And I'm trying to pause it.